saying anything that you don't want to go public. So I'll wait a bit. All right, guys, so we get started now. Fine-tuning is part of a broader picture, which is called transfer learning. Let me explain the concept of transfer learning today and put fine-tuning within the context of transfer learning. See, in machine learning, the typical phases that you go through in training a model is you would take an algorithm. Let's say that you have an algorithm. Take a very simple example. You have some model. That model could be, let us say, linear regression. Linear regression, or it could be all the way to a neural net. It could be any one of those. What you have is two sorts of data sets. You take a data and you split the data into at least two parts, training data and the test data. And what you do is you hide some part of the data, the test data in particular, you hide it under the pillow. The pillow, metaphorically speaking, you do that. And then you take the training data and you show it to the model. You give it. The training data will typically contain an input, which is represented as an X vector, but typically we don't, in our field, we don't put a vector symbol on top of it. So when we say X in this field, we assume that it is basically many features. For example, if it is a California housing, then it is the square footage, it's the location, it's the, and so on and so forth. Many, many features. They form the input. And then you have the output. For example, in California housing, the California housing data set, which most of us are familiar with, and I'll give a very quick thing about it. The inputs are, what are the inputs? It is the location characteristics. It is the square footage perhaps. It is then other characteristics like etc. And then what is the output? Output is the house price, prediction of the house price. How much did that house cost on that block, right? So when you train a model, you're basically making something like a Zillow. You show each of these items, some of the data, one input and output. So X goes in and the prediction that comes out, predictions in our field wear a hat. So it is Y hat, a Y hat comes out. Now, because you know the answer in your training data, you know the answer, right? So you can make a table and you can put your Y hat next to it. These are your predictions. And because you have a prediction, you can find out the error. How much is the mistake the model is making, which is Y minus Y hat, isn't it? Is equal to Y minus Y hat. So for example, if the house price was $100,000 and your algorithm predicted $130,000, then you do have an error of about $30,000, isn't it? That's your error. And then what do? The error helps you create what in our field we call the loss function. The loss function, for example, loss function. It is a measure of the total error that would be summed over all the data instances, Y minus Y hat, right? In this particular case, because it's regression, you can just take the sum squared error, right? In the very simple situation, this is your sum squared error. It's mistakes that the machine is making. And then in the beginning, when you give the data, the model is not trained. So it will make lots of mistakes, but gradually through gradient descent, through a process of gradient descent, your parameters, all the parameters of your model, for example, for linear regression, it would be theta naught plus theta 1, x1 plus theta 2, etc. So all of those parameters, they learn because you compute the gradient descent with respect to the theta of the loss, the derivative of the loss with respect to your parameters. And the gradient descent says that the next value of theta is the current value of theta minus a little bit of an improvement, which you get from this. So this is a recap of how machine learning works. In fact, what you're looking at is the learning. The learning of machine learning is this equation. It says that gradient descent is the process by which machines learn. Right? Now, everything gets sophisticated. These days, linear regression is not where the state of the art is. It has become very, very complicated neural networks. As you know, one of the godfathers of neural networks, Geoffrey Hinton and Hopfield, both of them just got the Nobel Prize for of physics. Right? And so in some sense, it is very applied physics, the sort of equations that I wrote on the right-hand side of the board. A physicist would be very, very comfortable seeing such notation. Now, you're also familiar, but if you're not, don't worry, because this will not deter you from making progress in this course. But it suffices to say that the training journey is, simply put, you show the model the data and you ask it to make better predictions, to align y. You're basically saying align y, your predictions to the y, to what we know to be true. And so once you have that, you have what you would call a trained model. A trained model is essentially a fixed set of parameters. You have found the optimal parameters that will make good predictions. Whatever the model is, at the end of the day, a model is built out of parameters. A good intuition for a model is to think that it is a box with many knobs, a radio with thousands of knobs. Right? For example, if you're used to your radio, you have one for volume, one for I suppose the frequency, FM, and so forth. So, and the same way, a training machine learning model is a box with lots and lots of knobs, and each of the knobs is a parameter. So these are the optimal trained parameters. So when people talk of a trained model, what they mean is a box of parameters, discovered best parameters for that model. And for the sake of this course, we will exclusively be talking only about neural networks. So we have that. How do we know that the model actually works? What you do then is you pass not the data, but you pass the test data into the model, and you validate that y and y hat is approximately the same as y, coming even on the test data, isn't it? Now, why is it that you split the data into two parts? You do it because these machine learning models can be extraordinarily clever. There are two ways that it can fit to data, or it can make good prediction. One is that it can just memorize all the values, right? It can remember that for a given input, this is the output. And every time you give it the input, it will produce the right output. So in machine learning, the two extremes are models memorize the data, or a softer form of it is overfit the data. B, it can generalize from the data, i.e., learn from it. Now, B is what you want, right? Ideally, you want your model to do this, but at any given situation, when you train your model, it would have done some part of A and some part of B. You want to maximize B, generalization, because learning is generalization. Or another way to put it is memorization is the enemy of generalization or learning. Right? There's a close parallel to that with human learning also. You have all been through college experience. And if you remember, if you find that a professor tends to repeat the questions in the exam over and over again, so what happens is college students are clever. They will soon develop a question bank in which they know what are the important questions and what are the perfect answers to those questions. And if the professor regurgitates the questions in the exam, as all of you can speak from experience, you're highly tempted to just memorize the answers to those questions and save the time and put it to better uses like playing cricket or watching movies. Right? So that is memorization. Now, you don't want your model to do that. So you want it to really generalize. So what you have to do, you have to let it know that you will test it on questions that it has never seen. And that is why you do a split between training data and test data. Test data you hide under the pillow. And when the model claims that it has learned, you test it against the test data to make sure that it truly has learned, because test data is something it never saw. So if it can make good predictions on the test data, it means that it has truly learned to generalize from the data, and some learning has actually taken place. So this is your classical machine learning paradigm. You have, when you have that, you have a test. The three phases are train, test, or validate. And then finally, that model is taken to production. You have a trained model and validated model, trained, validated model. You put it in production, and then you give it an unknown X in production, maybe coming from the user, coming from real life situation, real world. And then it makes a prediction, and that prediction broadly you trust to quite a extent. You trust that it is making good predictions for you. Right? So this is the cycle, and this is called the inference phase, inference mode. The difference between a train mode, test mode, and inference mode is in train mode, the parameters can change. The thetas are making their journey towards the perfect theta. Right? The parameters are gradually learning to be perfect, pick up the perfect values. In test, you ask this question, is it good? And here, theta, all parameters are frozen. Frozen, i.e. model is frozen. You don't change the model itself. It is just making inference. You don't let it learn from the data at all, right? In a traditional phase, unless you, of course, are doing something called online learning, which frankly, for very large neural networks is not feasible. So now comes a problem. You can do this. So there are two phases. You train the model in the lab, and then you deploy it for inference. Now, what happens is that there is a fact, it's called the neural scaling laws. Neural scaling law was discovered around 2020, but its effect implicitly was visible even before that. The history of our field is this. People started creating neural networks, the likes of Hinton and Jan LeCun. They were persistent, and Benjio and many other great researchers. They were very persistent. They believed neural networks represented a fundamentally powerful machine learning algorithm. But the field itself had its winters. There were many cycles in which people thought neural networks are a waste of time and that they can't do much. Fortunately, these great luminaries persisted through all of that. And so around the turn of the century, around 1998 or so, very early on, I mean, the first 1989 is when the handwriting recognition demo of Jan LeCun was there, which you can find on YouTube. Amazing. And after that, things only got better and better and better with this neural networks. But somewhere implicitly came the fact that, and in those days, for image recognition, pattern recognition, you would use convolutional neural nets, CNN. They were the architecture in favor. People were already noticing come around mid-20, around the 20, from 2012 till 20, let us say, so till today, one of the common observations has been that the bigger you make the CNN, the bigger you make the neural network, the better it does at image tasks, okay, and audio tasks. Somewhere along the line, obviously, came another architecture, the transformer architecture, or attention-based. Sorry, I apologize. This is jumping. Attention-based architectures. Transformer in particular, 2017, December 2017, it came. And after that, transformers have essentially taken over, at least in natural language processing, and to a large extent in computer vision also, image processing task also. But a realization that came is the bigger you make the model, so there are three parameters: how much data size, training data size rather, model size, that is the number of parameters in the model, and the compute. So what happens is that the neural scaling laws say that you need to increase all of this proportionately. If you make your model bigger because you realize that bigger models give you better results, better performance, you need to bring more data to the table to train that model. Otherwise, if you give very little data, the risk is that you'll overfit to it. Right? That's a broad picture. Obviously, there are caveats to it. For example, now we have discovered a phenomenon called rocking, which means that sometimes these large models are extraordinarily clever in generalizing even from small data sets. So that turns classical machine learning on its head, or some parts of it. But leaving those extraordinary things aside, general belief is you bring a bigger model, you need more data to train it. And not only do you need more data to train it, you need to train it for much longer time. Right? So more data means each of these, if you make the model bigger, if you make the model bigger, what is happening? Excuse me. If you make the model bigger, you need to make training data, and these things more computes, more iterations. The more time you have to spend training the model, right? More number of iteration, compute, number of steps of training that you need to do in the gradient descent phase, right? So there is a practical problem though. If you need a lot of compute, you need a lot of hardware. And then soon what began to appear is that the amount of hardware needed to train the model was not something that you and I have access to. We couldn't do that. So starting with the CNNs, for example, going back to ResNet, what companies began to do is that they would train a model with lots of data. They would do this. Train a big model with lots of data and compute. But they would do it in such a way that they would create something called a foundational model. What does that mean? One example is you can take a data set called ImageNet, for example. ImageNet is a collection of vast quantities of pictures of just about everything, from boat to houses to flowers to bees and to birds and everything. Right? Every possible thing that you can imagine, you have an image there. ImageNet was obviously is very, very important in the development of our field, and ImageNet was actually developed right here at Stanford with Fei-Fei Li. So when you train a model to recognize images, and so what you do is you tell it, this is a bee, this is a picture of a bee, and then after a little while, the machine begins to know that, right? And if you give it any other picture of a bee, not in your training data, it is still able to tell that it's a bee. right? What you have created is a foundational. What people would do is they would release the foundational, release the foundational model. And typically, they were kind enough to release it to open source. They would make it public. And when you make it public, you could go to, for example, PyTorch or Hugging Face Hub. These are places where you go, public sites, and you can just go download a model from there. When you download a model from there for your task, what do you do? You look for a model that is very close to the task that you want to fulfill, a foundational model. And once you get a foundational model, now comes a choice. You can just use it as is, and if your work gets done, it's awesome, right? You don't need to do any further. Let's say that you want to write a classifier that tells a boat from a truck, two different things, right? Or tells a cat apart from a dog. And so when you get a foundational model, you'll realize that it is doing a pretty good job of it. So in your business case situation, that's all you needed. So you're fine. But then sometimes what happens is you find that these foundational models, they almost solve the problem, but don't quite. So for example, it's able to recognize a car, but it is not able to tell that this is model X and that is model Y. And that is model Z, right? Three different models, X, Y, Z. It's not able to tell them apart. So what do you know? You have a foundational model that's good enough to know a car is a car, but it's not able to tell the specific models apart. So then what you do is that you do this thing called fine-tuning, which is the context of this course. You do fine-tuning. You go and get data, which is the supervised data, supervised learning with labeled data. Means you can go get a model car, XI, and then you can give it a label. You can say this car happens to be a Ford, let's say a Mustang, right? This particular car with these characteristics happens to be, let us say, it happens to be an Infiniti QX, let's say 56, right? And this particular input of data image that you have, it belongs to a car that happens to be a Toyota Camry, right? And so on and so forth. So what are you giving? You are giving it X and Y, labeled data. Y is the label, isn't it? And then what you do is you take this model that you just downloaded. The word people use is a pre-trained model. You download a pre-trained model, and then you further train it. You give it xi, you let it predict yi hat, but you happen to know yi, and so you create a loss function based on yi hat, and you do the gradient of that and back propagate, and then you further train the model, further fine-tune the parameters. Now, you might say, why am I doing this? Why don't I start with a model from scratch? And the reason you don't want to start from scratch is this foundational model has already learned a lot. It has learned to understand images. It has learned to recognize cars. It has learned to recognize that a car is different from a bee or a dog, right? So it has a lot of visual understanding, right? It's a machine that's really understands things, pictures of things. So you want to start from there. You don't want to start from scratch. You just want to take it the last mile journey. So in other words, you want to do a last mile refinement in its learning, and you want to say, be able to tell a Ford Mustang apart from a Toyota Camry or an Infiniti. Does that make sense, guys? And to do that, you start with a pre-trained model, and then you give it labeled data. Now, here is the good news. To pre-train a model, especially a large model, takes, as we just said, it takes a vast quantity of data, vast quantity of compute, isn't it? That's what it takes that you and I don't have access to. People use the word web scale. You need data at a web scale sometimes, right, to train these models. And the compute you need is enormous. Here I took the example of computer vision. Let's shift to natural language processing. In the natural language processing these days, you keep hearing about Llama 3.1 and so on and so forth, these open source large language models, which have a pretty good understanding of human language or languages. Right? So we use the word nowadays, not natural language processing, but natural language understanding, because these transformers, these large models, can understand human language. But to pre-train the Llama took hardware resources, the amount of compute resources that Meta or Facebook threw at it, the Facebook research lab, AI research lab threw at it, was in the order of billions of dollars. So just pause and think. A model that was pre-trained, to create a pre-trained Llama 3.1, you had to throw resources or requisition resources within your company for a few months of worth a couple of $1 billion, right? Or $1 billion or something like that. You and I usually don't work in companies where we can just put in a ticket to IT and say, hey, by the way, can you allocate $1 billion hardware resource for my project? They're just going to ignore it. First, they may not have that resource. And even if they have it, they will obviously be very surprised at your request. Right? So these pre-trained models are trained with a tremendous amount of compute resources. And what about the data size that went into the training of Llama 3.1? You can rest assured that it was trained with just about everything the researchers could scrape off the internet. Everything that you can imagine, every web page, every image, every web page, every piece of text that is there. I would imagine every Facebook message also must have gone in there, though I'm not sure. But it was trained on every piece of text that they could possibly get their hold of. And in fact, all the text that humanity has produced and put in the public domain was not considered enough. To train Llama 3.1, for example, they had to artificially generate data, further data, just to feed the beast, the hungry beast that was being trained, right? And at the end of all of that, they came up with the Llama 3.1, a pre-trained model. So the lesson is to pre-train a foundational model, you need extraordinary resources, extraordinary hardware resources. Only the hyperscalers have it. Yeah. Ginormous data. Right? Now, the data typically is unlabeled data. Right? So suppose you scrape the text from the web, then you don't have it. Nobody has put a label to it, what it is. All you have is scraped text. So what you do is you train the model with a task which is very simple. For example, you may have the sentence, the cow jumped over the moon. And so what you do is you give the machine only this much of the text input, and you ask it to excuse me 1 second. You ask it to, okay, this is misbehaving, but you ask it to output or predict output. You say, if I give you the cow jumped, you should come back and say over the moon, right? So that's how you create implicit level data to train the machine, which is not real level data. And then you pre-train the machine. But then in fine-tuning, what you do instead is, suppose you want to fine-tune, you give it a much smaller amount of labeled data. You give it genuine labeled data specific to your particular problem domain. Are we together? Now, guys, this OneNote is misbehaving. So let me restart it.
Hey, Asif, I have a question. Is that okay if I ask?
Yes, please do.
Yeah, so I mean, so two things is like, pre-training unsupervised data, supervised data label. I mean, are we categorizing them along these lines, labeled data and supervised learning and unsupervised data pre-training? The association seems like kind of forced a little bit. So I mean, I do agree with the fact that the ginormous data that is required to basically get every data and then kind of feed the what would come next kind of thing, and then go like continuously trying to like learn that whole process. But companies like newer companies like I forgot their names. I think it's like Upstage or something. I think I spoke to them recently. So those folks are all thinking that pre-training of a smaller model for with a specific kind of data would unlock more potential than actually fine-tuning. I mean, do you have an opinion on that? And we don't have to, go deep into it, just asking, that's all.
Yeah, no, that is a good question. So first, let me clarify this whole uh, thing about supervised versus unsupervised. See, in reality, you only do supervised training, right? Because these models are outputting something. Whenever a model outputs something and you have an expectation of what it outputs, inherently it's a supervised learning or it's a predictive model. No, it has to output. That output is its prediction, and you compare it with the ground truth. The thing with pre-training is when you take a large model and you pre-train, you have to artificially create a split in the data. Like, for example, a sentence like the cow jumped over the moon, you take a part of the sentence and the remaining of the sentence becomes the prediction, right? So out of just unlabeled data, you create in effect input output prediction, labeled data, and then you train with it. Then when it comes to fine tuning, then you need genuine label data, of course, because you wanted to tell a Ford Mustang or an Infiniti and a Toyota apart if you're doing images, or let's say you're doing finance, right? The word bull and bear have a different meaning in common language, but in finance, the word bear market and bull market have a very specific meaning. So you can fine tune a model to recognize the nuances of the financial world. So there, fine tuning makes a lot of sense. Now, fine tuning also takes much less hardware. So I'll finish that thought and then I'll answer the remaining of your question. See, when you fine tune a model, the data set is small. The data set for fine tuning is much, much smaller than the data set for pre-training. Much smaller by orders of magnitude. So for example, this may be petabytes of data. And this may be just a few hundred or thousand records. right? And so because the data set is small, and because you're just doing small perturbations in the parameters, small changes, you can actually do it on a much more modest hardware. You can do it, for example, on a single machine with, let's say, 8 A100s, right? Or sometimes, as in the course of this course, you will notice that even the RTX 4090, which is what support vectors clusters has, uh, bank of, and you'll be working on those, is more than enough. In fact, you'll be able to fine tune on your laptop also, if it has a GPU, right? So fine tuning takes a lot less resource. Now let me address the question: should you fine tune, or should you fine tune a much bigger model, or should you should you completely train a model from scratch? Right? That is a question. It's a recurring question. It keeps coming up. See, the choice ultimately becomes, do you want to piggyback on the work of others, or is your problem so unique that it is better that you build a model of your own? So here are the trade-offs. Or from a mathematical perspective, here is a way to reason about it. See, every data has a probability distribution. So suppose this is the data in the wild, data for pre-training. It has a certain distribution, right? So for example, there may be lots of cats, less number of giraffes in the data. I'm just making it, dummyifying it down, but just to give the intuition. The probability of a cat is much higher than the probability of a giraffe or something. This is the probability of X, right? And this is X in some sense. Now, when you pre-train, the only reason you would want to fine-tune is because this is not how your data, for which your special purpose within your company or whatever research project you're doing, its data distribution may be slightly different. It may be somewhat like this. So you can notice that there is a slight difference between this distribution, the blue distribution and the yellow distribution. But the general idea is that those differences have to be relatively small, right? So you're doing a small adjustment. Are we together? Your data distribution, Pete, let me just write it down here. Your fine-tuning data set is a probability distribution is only slightly different. Another way of saying it is, a very intuitive way of saying it is that your fine-tuning data has to be different from pre-training data. Otherwise, there is no point in fine-tuning. The model is already trained on the original distribution. But your distribution cannot be wildly different. So for example, if it is the case that your data set looks like this, its distribution is completely different. Do you notice that? If I actually, let me use a different color. Let's use this color. Something like this. So now you notice that there is a vast gap between this and this data. Now, the more you try to reshape the machine, a neural network, to go from learning on the blue data to learning on the orange data, the more you have to put in effort. You need to bring more data in, you need to train it for much longer, and you ultimately reach a point that why exactly am I fine-tuning? So the yellow is the situation where a fine-tuning is warranted. The orange is a situation where a full training is warranted. Are we together? You must fully train the model because the model has been trained on a completely different reality than your reality. If your reality is so divergent, then you should not start with a foundational model. Or another way to put it is that your situation is so unique that a foundational model, which is adjacent to your use case, does not exist. When that is the situation, then you have no choice but to completely full train a model. But when you full train a model, then the considerations that come in are that do you have the compute budget to do that, right? So you may First, you have to, what is your data set size? So full training begs this question: how much data do you bring? And the second question that it raises is, how much compute do you bring? And based on these things, these two levers determine what is the size of the model you can, in practice, fully train. Generally, the answer to that is you will bring at most 10,000 or 100,000 a data set of that size. And you will bring in a compute, which obviously has to be proportional to the data set you bring. And so you can start with a small model. Practically, what you will end up with is a small model. But see, a lot of these decisions, should you fully train a model or should you fine tune? Mathematically, it is a no-brainer. You just have to ask this question: how different are the probability distributions between your data set and the original data set on which the machine has been trained, pre-trained? If they are divergent, a pre-trained model is useless. In fact, there is no pre-trained model, foundational model, that is adjacent to your use case. So you have no choice but to fully train a model. Then bring your data, bring your compute, stare at it, and use the neural scaling laws to determine how big your model should be. So that is the right way, I suppose, to answer the question that you asked, Aaron.
Thank you.
Sir, quick question. How do you mathematically define this? Can I say if the distribution mean, mode, median won't coincide, then we have to fully train it? Or if they coincide, then we can use the model. How do you mathematically use the language? Or can I say like right skew negative?
Yeah, that's a very good question. See, given distributions, right, there are measures of divergence. For example, KL divergence and so on and so forth. There are a distributional divergence, but I'll give you a very common sense approach. So project your data into 2 dimensions, right? Using some method, UMap, PackMap, whatever it is, use it to project your data into 2 or 3 dimensions that you can physically see, right? And you always know what the pre-trained data is like, web data is like. Look at the two. Yeah. Does your data, the pre-trained data that is out there, more or less we know its distribution. Right?
We can see hills and valleys kind of thing, sir.
Come again?
We can see hills and valleys like when we see in global minima, that kind of thing.
Yeah, no, it will just look differently. For example, when you project it in 2 dimensions, if you notice that most of the web data is like this, right?
Yeah.
It is scattered like this. I'm just giving an example, right?
No, yeah, this is good.
Clusters here. But your data looks like this.
Yep. Yeah, got it, sir. Got it. Yeah.
So what can you tell between these two? Just stare at it and you can tell, oh, my data is so different, isn't it? So when you encounter this sort of a situation, you know that there is no point in starting with a foundational model which has been trained on the purple data, the web type data. There is no point. At that moment, you should start with a new. So that is a sort of a very realistic or down-to-earth way of deciding between full training and fine-tuning. Right?
So I have a follow-up question. So if I am choosing a model to fine tune on a specific, give it a like a to perform, make it perform a specific task or a set of tasks that is super special, and I can come up with like a less amount of data to basically fine tune and give it that pull that thing that you said between the yellow and the blue and make that happen. So how do I choose? Like, I'm coming up with a label data, like say 1 million of them, and I want to like now fine tune it to give this the extra ability for the model to basically give better better results. So how do I choose what model to fine tune?
Okay,
that
you
choice.
always look for, sir, you always look for the closest foundational model that is out there. And generally, that will be through experience, I mean, through knowledge, through a common conversation. You would know, let's say that you're talking of natural language tasks,
Got
right?
it.
Then you would know that people are very public. Like if you go and look into the Hugging Face, there are these things called the model cards.
Right.
Right? And you can look up, but then there are gazillions of models there. What you really do is that, see, we all don't work, like any work is not done in a vacuum. So what will happen is, if you're doing a work, other people have been doing adjacent work.
Right.
My approach, so I'll give you the way I do it. I just look up the research papers that those people have been writing.
Okay. Yeah, right. Yeah, I look at model cards and some of their sample training data to say like, okay, this is using like a lot of text to code, and then I probably pick up that. That's, yeah.
Yeah, that's that. And see, sometimes you may pick a foundational model, and then there may be an even better foundational model much closer to your problem set. And then you may go, oops. But at the end of it, see, practical reality is that if you have reasonable amount of data and you take any model that is near enough, close enough, a foundational model to your problem, and you fine tune it. If you fine tune it well, it'll work, right? And my way of doing it is I just start reading research papers in that area. And then I come to know just about every model, relevant model that exists. Obviously, literature survey is a science in itself. And if you want to know what is the right way to go about it, there is a whole process. It's called Prisma. For you, I'm saying this specifically for you, Arul, because you are in leadership role, and I'm sure quite often you have to do a literature survey to figure out what is the best approach to take, or what is known and what is not yet known. So follow the Prisma process.
Great. Thank you. I think you mentioned it in our other training.
Yeah.
Thank you so much.
Ahmad, you have a question with your microphone on.
You basically doing a lot of work with actually showing the foundational model. So if you go onto any Hugging-based model now, it'll show the data set that it was trained with, if possible, and the foundational model.
That's right. That's right. So you see that. So yeah, there's a wealth of information. And generally, Arul, at the end of it, it comes down to, right, you can do all of that, or you can make a phone call to your friendly expert nearby, right?
What were the questions, sir? What did Hamad ask?
Hamad didn't ask a question. He just mentioned that in Hugging Face, there is a wealth of information in the model cards.
Correct. Yeah, you can actually see what data the model is trained on.
Right.
Yeah. So, and then
that.
you can, the way you described here very nicely, you can project in 3-dimensional space, and let's see if it coincides with your data or not.
That's right. So guys, that is it. So let me bring it all back together and summarize what we learned just now. What we learned is this. What we learned is today, as the neural, there's such a thing as the neural scaling laws. It is a fact of life. We don't know. We don't seem to have a way around it. What we have found is you make the neural networks bigger, then you need to bring more data, you need to bring more compute, and then that model can be properly trained. Why would we want to make the models bigger, to summarize? Because we found that bigger models just perform better. There is no way around it. People are trying to find all sorts of clever ways around it. But broadly speaking, the trend remains, right? Bigger models are better. Now, it just so turns out that every time you create a bigger model, people then ask this question, can I make smaller models as capable as the bigger model? Can, in some way, using some technique. That is a whole active area of research. And then what happens is people come up with very clever techniques to take the same performance of a bigger model in orders of magnitude smaller model. But then those techniques are also being used in the bigger model to make them even better. Right? So it's an unending cycle The bigger models keep evolving, the smaller models keep evolving, techniques keep growing, all of that keeps happening. But let's go with one basic summary. Bigger models are a desirable thing because they perform better at most tasks. But because bigger models cannot be trained by you and me, there is this whole field or the whole practice of transfer learning. And let me put this word in the first concept that we are putting on the table, transfer learning. It has become the new norm. Transfer learning says it is this journey, pre-train a foundational model, let me call it M0. Pre-train a foundational model M0. Next is use it. If it works for your problem, fine. This is your transfer learning journey is done. Just use it for inference, right? On the other hand, use it means inference mode. If not, fine-tune the model. Are we together, guys? You fine-tune the model. So in this thing, we have come up with a pre-trained model, a foundational model, or a pre-trained model. Now, it is there. It has been a common practice now for many years. Most of us, when we do computer vision tasks, we go and get ResNet 50, ResNet 102, or something like that. We work with VGG, we work with Inception or something. And most of the time, just using the model out of the box is good enough. But when it is not good enough, you can fine tune. Now, CNNs are gradually getting increasingly displaced, and transformer-based computer vision models are coming in gradually. And those two also, I mean, it's a mix. At this moment, you use both CNNs and transformers. Transformer models are even bigger. There also the same thing applies. And for natural language processing, transformers are practically taken over. Most of the new architectures are transformer architectures. So there, you download a pre-train. When you get a bird or a distal bird or a Roberta, what you're doing is you're downloading a pre-trained model, right? And then for your particular purposes, you fine-tune it. Now, here is the main value proposition for fine-tuning. See, what happens is when you fine-tune a model, the model has done most of its learning. You know, it's almost like one close analogy to real life is you're trying to hire an employee for your company to do software engineering. What your company does is something very proprietary, right? It has its own libraries in Java and Python and C++. Your choice is you can start with a baby, teach the baby English, teach the baby everything needed to make into a computer scientist and a software engineer, right? Or you have a choice, practical choice. You go and get a computer science college graduate. Common sense says that you would do the latter, isn't it? That is the closest analogy you have to transfer learning. What you do is it takes a ginormous years of effort to create a well-educated computer science graduate. You don't want to lose that understanding, that experience hard-won through lots of projects and homework and coding assignments and whatnot, right? And prior to that, just learning the English language and math and physics and whatnot. You don't want to lose that. You don't want to retread the entire territory in-house by taking babies and growing them up into computer scientists over a period of years, isn't it? So that is the main value proposition of fine-tuning. You're saying, let's not lose the benefit of all the learning the model has done. Let us just fine-tune it for a specific purpose. Albert, you have a question?
Can you hear me?
Yes.
So what happens if I fine tune a model and something comes better, the foundational model comes better? How can I re-script the whole tuning process so I can apply to the new model?
Yes. So, so Albert is asking a question. Suppose you take a foundational model. Let's take it like this one. You have a foundational model F1. You fine tune it to get F1 fine tuned for your purpose. But then the company releases F2, which is better. What you have to do is you have to compare these two. Right? If F1 is better, you stick with it, but nevertheless, you start a new journey to fine tune F2 fine tuned. Because you know that if F1 fine tune was good, F2 fine tune will be even better. Right? So you start this journey, but you can still continue using F1 fine tune till your F2 fine tuning is done. If you find that F1 fine tuning is inferior to F2 fine tuning, well, of course, you throw F1 fine tuned out of the window. You start using the F2 foundational model till you have fine tuned the foundational model to your needs.
Is there a way to script the whole thing?
No, script means you have a pipeline. In the MLOps course, you learn the pipeline.
Okay.
So you just feed it through the machine learning MLOps pipeline. It goes there. So I will tell you a story because one of you, Arul, I think you brought about this whole question that isn't it a good idea to train a foundational model from scratch, your own model from scratch? So I would like to bring up the case of Bloomberg in finance. When GPT 3.5, the first chat GPT came out, Bloomberg, which only deals with financial data, at that time, there was not as much clarity what to do. So they thought, why don't we create a foundational model for finance itself? Right? Just like GPT 3.5 is a general purpose model, let's create a foundational model for finance. So what they did is Bloomberg holds on to a vast amount of financial data. What they did is they took all the data, the architecture of obviously GPT 3.5 is public. We all know, broadly speaking, what the architecture is. So Bloomberg, it's a very good case study. Bloomberg created a foundational model for finance. And what they found is the foundational model for finance, which is basically like a GPT 3.5, but specifically trained from the ground up, fully trained, not fine-tuned, but fully trained for finance, right? So let me call this model the Bloomberg model, BM, Bloomberg model. Then GPT 4o came out. A few months later, GPT took about, I think, almost a year, but GPT 4o came out. Guess what happened? Can anybody guess? Which would be better? The Bloomberg's model, which was from the ground up trained on financial data, would that not outperform only in the financial domain? Because you're laser sharp focused only on the financial domain. So your common sense says that it should do better than the next general purpose model, let's say GPT-4.
GPT-4 would be far superior
Why is that?
because it has other ideas and other things that come. So
That's one answer. Anybody else would like to answer this? What do you think would happen? A foundationally from the ground up trained model specifically for finance, would it not outdo any general purpose model? Any other opinions, guys?
So maybe the data surrounding the finance events and stuff cause influence on the finance itself. So GPT models take a lot more data than what finance alone takes in.
Right. So see what happened is, and it took people by surprise, actually. Even I wasn't sure what was going to happen. The GPT-4o did better on finance than the Bloomberg model, right? And that had the researchers scratch their heads. Why? now we have some partial understanding of why. Nobody fully knows because none of us really know how these AI models truly work. We don't have a mechanistic understanding of their brains. But here is what we think happened. GPT-4o better understands human language, the meaning of things that we write. It has an even deeper understanding of it. And that deeper understanding gave it more tailwind, more advantage than a smaller model like 3.5, which was specifically trained only on financial data. So from that arose a wisdom which sort of relates to what Arun was saying, namely that a general purpose bigger model outperforms often, not always, often a smaller specialized model. Because today, and the reason, and by the way, this is true in 2024, but may not be true later on, because it turns out that these models, they still have only a partial and imperfect understanding of human language. So the bigger brain you get. So in other words, what is it trying to say? Neural scaling laws win. Win over specialization. Isn't it? If you are given a choice to make it bigger or to train a model the same size but with specialized data, go bigger. Right? That seems to be the big lesson. And therefore, and this is something that you need to know. Bloomberg actually did a post-mortem, and they were very kind, actually, very transparent. They made their findings available. So in their post-mortem, they said that in hindsight, we learned a lesson, and this is practically them. I suppose I'm rephrasing what they learned. And a very, very, very nice analysis, actually. And there's more nuances to it than I've covered, but you should go read that. So that is about the neural scaling laws. Now, with that in place, I would like to now talk about the benefits of fine-tuning. Right? Now we know what and then some challenges, and after that we'll take a little bit of a break. What are the key benefits of fine-tuning? One is adaptation to specific domains and tasks, which is the whole purpose, right? You take a model and you just fine-tune it for your particular purpose. Let's say finance, fine-tune it. Right? Till you have access to a bigger model, go fine-tune a model. Don't train a model from scratch. Improved performance on targeted applications, again, a given. There is resource efficiency compared to training from scratch. You know, if you train a GPT 3.5 from scratch, maybe Bloomberg can do it, but you can't. Right? But you can take a comparable model. You can take a Llama 3.1 and you can fine-tune Llama 3.1. Right? Which many of us will be doing in this course. You will learn how to fine-tune models. Also, you can iterate much faster. You will learn techniques such that if you have fine-tuned a model, let's take a very visual example. If you have fine-tuned a model to always to create a person with a, let's say, very Asian look, and then you have fine-tuned another little model which gives the person a very geeky look by making the person wear spectacles, right? Now you can take those two fine-tuned pieces together, model together, and compose a model that always produces images that look like very geeky Asians. You see that, right? So there is a composability to it, and you can iterate and you can move much faster. Fine-tuning, though, does have some challenges. So let's address the challenges that are there with fine-tuning. What are the challenges of fine-tuning? First is that fine-tuning takes a lot less hardware than training a model from scratch. Nevertheless, it does take significant hardware. How much hardware does it take to fine-tune a model? Let me give you an example. So suppose I have a model. These days, most of us work with 7 billion parameter model, right? 7 billion parameter. Let us say we are dealing with Llama 3.1. Is it 7 or 8 billion? Llama is 7, is it? 8 billion parameter Llama 3.1, right? Billion. So now remember that each bit takes 2 in a floating point F16, floating point 16, it takes 2 bytes. Right? So what it means is to load the model, you would need 8 cross 2 is equal to 16 GB of VRAM, that is the video RAM, the memory that is there in the GPU itself, GPU RAM. You would take. Add now, if you do forward inference on the model, you can add 20% overhead. So multiplied by 2 and 1.2, and this becomes, what does it become? 160 plus 32, 1.9, roughly speaking. Right? Am I right? 1.9. So it becomes 1.9, 19 GB, 19 GB, right? Plus multiplying factor of 1.2, 16, right? 1.2 times 160 plus 32 is 192. So 19 GB VRAM. Now, if you are sitting upon a RTX 4090, which is the graphic card most of us can barely afford and put into our computers, this is enough. You can do inferences on that at full precision. But if you want to fine tune, what you have to do is you have to open up the weights of the model. And when you open up the weights of the model, let's say that, let's take a case. Well, the simplest fine tuning is open all the weights, open all the, people often use the word weights, but what they mean by weights is parameters. Open all the parameters for further training, to change. And then you train the model, you fine tune the model. When you fine tune the model, every parameter, theta, ij, every weight, let's say in a neural network, these are the weights, ij, of a given layer L. It needs, as we realize, 2 bytes just to keep the weight. But because in the back propagation, you need the gradient of the weight, gradient of the loss with respect to the weight, you need another 2 bytes to store. And then because you have to optimize the gradient descent, the modern optimizers, they require the quadratic term also. For example, Adam requires the quadratic term also. You now require 2 more bytes. So all of it put together is 6 bytes. And so in floating point 16, so if you have an 8 GB model, an 8 billion parameter model, you need 8 cross 6 is 48 GB plus overhead, which will come to 54 GB. You realize that now you are in much bigger territory. You are in the territory of an A100, isn't it? You need a really powerful machine to be able to host it or fine-tune this model in the simplest form. Now, in this course, you will learn how to fine-tune the model without needing so much hardware. Actually, that is the thing that most people don't realize, that you can actually fine-tune models without using up so much hardware. In fact, you can do it on minimal hardware, which is, I guess, one reason that people who are good with fine-tuning, they are so much in demand, because they can, people who are smart at this game, they can save you a lot in hardware costs. That is what we will learn about it. But nevertheless, fine-tuning takes a lot more hardware compared to what? Not fine-tuning at all. So if you don't fine-tune the models or the large language models at all, what is your alternative? Is there a third alternative? See, you can't fully train the model. That is beyond you. Suppose fine-tuning is outside your budget. What is the third choice that you have?
Use it as it is.
Say that again, Gopal.
So use it as it is. With less
Use it
accuracy.
as it is. No, there's one more choice you have. use it as it is, but do prompt engineering,
Mhm.
prompt optimization. And this is a thing that obviously people miss sometimes, that the most free form of fine-tuning a model, literally, is to use prompt optimization. The model is producing something, but if you write clever prompts, if you do it well, you don't have to do anything to the weights of the model. You can leave it, but you can do prompt. So prompt optimization is a new frontier, right? You can change the behavior or the performance of a model simply through better prompts. Right? Obviously, we just finished a course, an entire boot camp on advanced prompting techniques. And properly stated, prompt optimization is one of the most successful fine-tuning techniques. Right? But it is a technique that we won't cover in the course except in passing, because we just had a full course on prompt optimization. When you do prompt optimization, you don't touch the weights you don't touch the model itself. Whereas this entire course is about actually training the model to better weights, better parameters. Right? So at this point, we have been talking for quite some time. I'll give you guys a 10-minute break. Is that reasonable? A 10-minute break. Let's have a coffee, etc. And then let us regroup. And I will then go into approaches to fine-tuning. Our next topic will be for today, and last topics will be approaches to fine-tuning. Fine-tuning models. And how many ways can you fine-tune models? But before that, I would say let's take a 5-minute break. 5 or 10 minutes.
10 minutes.
10 minutes. Let's take a 10-minute break. So by my watch, it is 8:40. Let's meet at 8:50. And while those 10 minutes are happening, if anybody, while everyone else is taking a break, if anybody has a question, please feel free to ask.
Kasif, I have one question.
Go ahead.
In one of your previous courses, you mentioned prompt engineering will also be automated by AI. So how far is it happening now?
Oh, we are there in the prompt engineering course. We covered dynamic prompt discovery using AI itself.
Wow.
The optimum prompt discovery. We already covered and finished that topic.
So in that context, then how relevant is fine-tuning with respect to prompt engineering?
See, the rule, that's a very good question. The basic rule is if you can get away with prompt optimization, it is the best, because then there is no cost to it. The problem with prompt optimizations always has been that the machine is very sensitive to prompts.
Mm. Okay.
And we are only now beginning to get a handle on it. Let's put it this way. Prompt optimization is a field that has just started, whereas fine-tuning is something that we have been doing for a decade.
Oh, wow. Nice.
So obviously we know a lot more about fine-tuning than we know about prompt optimization. We don't really know how these machines are thinking internally, which is what we need to know to do high-end prompt optimization. But nevertheless, prompt optimization itself is a subfield of fine-tuning.
Oh, okay. Thank you. Thanks so much.
Are you having fun?
Yes, definitely. All the things that we talk, like the nice summarization, is just making me link all the things that we have learned so far and be able to move further. Thank you so much.
You're welcome.
I may have to switch to phone for like maybe half an hour. I'll be on the phone. I had to just go out and come back, but I'll be on the phone. Thank you.
OpenAI models cannot be tuned at all.
No, they can't. They are not public models. No, see, so the question that I got from the audience is that can OpenAI models be fine-tuned? The simple answer is you and I cannot. But if you are a corporation and if you have an account in Azure, then they let you create your own fine-tuned versions of the OpenAI, right?
They're giving free credits, not that.
Oh, they're giving free credits according to Hamal to fine-tune and create your own little fine-tuned variants of the model. Yeah. But generally, it's a after your free credits are over, it's generally very expensive. It's a corporate game. But yes, you can do that. They do create fine-tuned versions of your model. And in fact, how they do it, we can pretty much guess because you'll learn those techniques in this course, Albert. See, another way to put it is that this course helps you save tons of money. You take a free model, fine-tune it, and it remains free. And in a way, going to OpenAI, which starts out with a paid model, and you fine-tune it and they charge you even more. So
Instructor jobs are fine-tuned. Like, is it instructor CLI jobs? Are they not OpenAI fine-tunes?
no.
Oh.